Introduction to Linear Approximation. As we have seen in calculus, mathematics are able to take the derivative of many different functions to compare related quantities that are changing over time. But what can we use derivatives for in the real world and how? By using linear approximation, also called tangent line approximation, we can zoom in so close to a point on a nonlinear function that the graph will look similar to a line. As a result, we are able to use the tangent line, which rests closely to the curve around a point, to act as a human calculator and approximate other local values along the curve, as long as we stay near the particular point.
Derived from point-slope form, the general equation of the tangent line L of x of a function f of x at x equals a is written as follows. L of x equals f of a plus derivative of a times x minus a. In other words, the tangent line equals f evaluated at point A plus the derivative of the function evaluated at point A multiplied by x minus point A. The steps to using this formula is 1. Find a point that you want to zoom in on. 2. Calculate the slope of that point using derivatives. 3. Write the equation of the tangent line using point-slope form. 4. Evaluate the tangent line to estimate another nearby point. We will now be looking at practice problems. In our first problem, we will linearize function of x equals 2x cubed at a equals 2 to approximate f of 2.1 using the formula that we just went over. For our first step, we find the point by plugging in a equals 2 into the function to find f of a. F of a equals 2 times 2 cubed, which equals 16. That gives us our point as 2, 16. In step 2, we find the derivative. F of x equals 2x cubed, which gives us 6x squared as the derivative. In step 3, we substitute into the derivative to find f prime of a. F prime of x equals 6x squared, m equals f prime of a, which equals 6 times 2 squared, which gives us 24. In step 4, we write the equation of the tangent line using the point and slope found in steps 1 and 3. As a reminder, point-slope form is y minus y prime equals m, which is slope, times x minus x prime. Once we plug in the numbers, we get y minus 16 equals 24 times x minus 2. In the final step, step 5, we substitute x equals 2.1 into the equation of the tangent line found in step 4 and solve for y. Y minus 16 equals 24 times x minus 2, which simplifies to y equals 24 times 2.1 minus 2 plus 16. Then we solve for y, which gives us 18.4. To summarize, using linear approximation, we find that f of x approximately equals 18.4 when x equals 2.1, which is more accurate than the 18.522 that we would get if we had simply plugged in 2.1 into f of x equals 2x cubed. As you can see, as long as we stay close to our given point, our linear approximation will be accurate, so don't stray too far. We will now be moving on to differentials.
Differential equations. A differential equation is an equation that has an unknown function and one or more of its derivatives. The solution to a differential equation is known as a function or a class of functions. Given y equals the function of x or f of x, dy and dx are both differentials, and their relationship between them is given by dy equals the derivative of f of x, which is represented as such, times dx. When given f of x, the dy differential is renamed to the df to represent the f function, or df, or y, equals the derivative of f of x times dx. You can think of dy as being the dependent variable and dx acting as an independent variable that can be assigned to any real number that isn't 0. Here's an example. For the function below, find dy and evaluate when x equals 5 and dx equals 0.2. We write out the function below as y equals x to the second power plus 2 times x. As stated before, y is equal to the function of x, which means we can use y and f of x interchangeably in our equation. Therefore, f of x is equal to x to the second power plus 2 times x. We then need to find the derivative of the function, which can be stated as the derivative of f of x is equal to d over dx of x to the second power plus d over dx of 2 times x. We start by using the power rule for the first half of the equation, which states that d over d of x to any function x to the power of n is equal to n times x to the power of n minus 1. For the second half of the equation, we use the straight line function formula, which states that the derivative of a times x plus b is equal to a, with b equaling 0 since it has no assigned value in this case. After doing these two steps, we end up with the derivative of f of x equaling 2x plus 2. The differential formula states dy equals the derivative of f of x times dx. And since we have the derivative of function f, we can use that value to come up with the equation dy equals 2x plus 2 times dx. Since we have the values of x equals 5 and dx equals 0.2, we simply need to plug those values into the equation and solve. dy equals 2 times 5 plus 2 times 0.2, which we could simplify to dy equals 10 plus 2, the 10 being derived from the 2 times 5, multiplied by 0.2. And of course, if we add 10 plus 2, we get to 12, which means that our final equation, or final part of the equation, would be dy is equal to 12 times 0.2. If we multiply those together, we end up with a value around 2.4. And that is it for differentials.